Bon, je vais commencer. Peut-être pour ceux qui ne me connaissent pas, je suis Jean-François Johanny et je remplace Bernard Derrida, qui est à l'origine de l'invitation du professeur Pastur, mais qui ne pouvait pas être présent aujourd'hui et donc il s'excuse de son absence ce matin. Donc le Collège de France est très heureux d'accueillir le professeur Leonid Pastur pour une série de 4 conférences sur les problèmes d'intrication dans les systèmes désordonnés. Professeur Pastur a fait la plus grande partie de sa carrière à Kharkiv, en Ukraine, où jusqu'au printemps dernier, il travaillait à l'Institute for Low Temperature Physics and Engineering de l'Académie nationale des sciences d'Ukraine. Il a été pendant une dizaine d'années professeur à l'université qui s'appelle maintenant Université Paris-Cité, mais à l'époque ça s'appelait Paris 7, et il partage depuis le printemps dernier son temps entre l'IHES et l'ENS. Le professeur Pastur est un spécialiste de la théorie des systèmes désordonnés, qui n'est pas du tout mon domaine de la physique. Il est mondialement connu pour ses travaux sur la théorie des matrices aléatoires, en particulier depuis son article avec Marchenko en 1969 sur les valeurs singulières des matrices aléatoires rectangulaires, qui est écrit en russe, d'après ce que m'a dit Bernard. Des travaux dont les retombées ont conduit à de nombreuses applications récentes. Il a beaucoup travaillé sur les verres de spin et les opérateurs de Schrödinger désordonnés. Il a en particulier donné la première preuve mathématique de la localisation d'Anderson à une dimension. Le professeur Pastur a reçu de très nombreuses distinctions en Ukraine et à l'étranger. Avant de vous donner la parole, pour tous les professeurs invités au Collège de France, je vais vous remettre la médaille du Collège de France.
Oh mon Dieu, merci.
Si je vais arriver à l'ouvrir, mais voilà. Au nom du Collège de France, je vous...
Merci, merci beaucoup, c'est un honneur et plaisir. Oui. Merci.
Voilà, et donc je vous laisse la parole pour vous.
Merci. Bon, tout d'abord, je voudrais remercier. Donc, merci beaucoup pour toutes et tous qui sont venus à mon cours. Et je suis également très reconnaissant au professeur Bernard Derrida et au Collège de France pour faire possible pour des honneurs et des plaisirs d'être un professeur invité ici. Et donc, le sujet de mon cours, c'est ici. Donc, à partir de ça, je passe en anglais. The subject of my course is entanglement in disordered systems, and here the short outline. Oui. Donc, okay, first of all, let me say several words. Maybe all the audience is more or less knows what it's about, and we know the quantum mechanics is absolutely general and quite precise theory, and quantum entanglement is a quite non-trivial phenomenon which was first somehow introduced by Einstein, Rosen and Podolsky in their famous paper of 35, but in that paper it was somehow invented by Einstein in the negative, to do something negative. He would like, he wanted to use this phenomenon to prove that quantum mechanics is not complete. But this very same year, Schrödinger understood that it is quite important quantum properties, and then for 30 years, more or less, it was sleeping. Next breakthrough was by John Bell, who first understood what is going on, because the argument of Einstein was that the only way for quantum mechanics to become some reasonable theory, it is to introduce so-called hidden parameters which should be somehow classical. And it was John Bell who first showed that it is not necessarily. And then next breakthrough was in the beginning of 80s when three persons that mentioned there from completely different 3 points of view just pronounced that this phenomenon is quite important to do something which is now known as quantum computers. From the theoretical side, it is quite active and interesting phenomenon. As for technological side, it is still quite questionable, but nevertheless. So it is in quite shortly, not too precisely, one can say that the entanglement is a quantum analog of statistical dependence in probability theory. As such, it is a bit strange that it took so much time to understand this. So it is a special kind of correlations in quantum systems, and now it is, if you look at the literature, current literature, you see that there is thousands of papers treating quite wide range of problems related to entanglement and quantum computing, etc. But not only that, because it turns out that it is important in quite fundamental question how when we get statistical mechanics. It's called entanglement. It's called it's thermalization, and then quite unexpectedly it played quite serious role in the subject which is around the black holes, and I will try to explain the simplest model that was there. And it is the program of the course. Today it will be mostly, so there will be 4 lectures. They could not precisely correspond to this subject because maybe some of them I will manage to do a bit shorter, more longer. But basically, as for subject, these are 4 subjects. Today it will be just introduction, and if I'll have time, I'll discuss this toy model of black hole radiation. Next subject is quite simple. So this all the field related to entanglement, motivated and hopefully will be applicable to quantum computing. It is about qubits, the simplest quantum system that I'll discuss later, but somehow the field is divided roughly in 2 parts. One of them is dealing with 1, 2, 3, 4 qubits, just to try to understand what is going with this with entanglement in this simplest setting. And second, when you have big number of qubits, which is somehow seems more close to the subject, because if we hope to have reasonable quantum computer, this computer has to contain thousands, maybe millions of qubits, like standard modern supercomputers. They also have millions of bits. So it will be the second subject, mostly about 2 qubits, and we'll see a lot of quite unusual phenomena. And the next, third and fourth, which is about entanglement, when you have a lot of qubits, and it's a lot of qubits. In that case, the third subject, it was mostly review what is going on in that field, and the fourth one will be about the quantum system in a disordered environment, and we'll try to take into account Anderson localization to see what will happen, because previous 3 subjects, they will be mostly about translation invariant case. Today, not today, but the first part is like that. The first, it will be just few elements of quantum mechanics, which maybe all of us you know, but I just need to establish certain notations and terminology. Then, okay, I'll tell several words about notations. Roughly speaking, it will be just a little pieces of linear algebra in Dirac's notations. And then it will be quantum mechanics 2, where I will introduce the entanglement and what is simplest things with this important property, quantum property. And then this will be this toy model just to show you that not things that I will tell you before, they are not too, so to say, abstract and academic, because there is a quite interesting and quite popular model of black hole radiation, which uses the random elements, in fact, random matrices, so very simple form. And here you see, I'll describe the models and roughly the results before, and then more or less modern form, which uses the random matrices and allows us to make more complete form of that model. Yes, okay, and so to say quantum mechanics 1, I'll start from very general thing. One can present a kind of scheme which any physical theory that pretends to describe the world should consist of 4 elements, very schematically, very general. So the first we have to say what are the states in that scheme, in that theory. That means how do we describe our phenomena and things. And second, we have to say which quantity we are going to measure, to deal with. Third is how do they develop in time. And fourth, of course, what is the measurement? How to measure these things, observable, which we are interested in. Coordinates, moments, magnetic properties, electric properties, etc. Well, and just to illustrate you, the scheme is quite reasonable. Let me show you this table in which I just presented 2 quite known fields, classical mechanics and quantum mechanics, and what are implementation of those 4 items of general scheme of any physical theory. So the first, of course, you'll see there is a lot of seeming similarities. So first is, what are the states? There are 2 types of states. There are pure states. These are just points of phase space. Phase space roughly is just coordinates and momenta. Then, and this was introduced by Newton. And in quantum mechanics, pure states is a vector of so-called state space, which is a Hilbert space. We will deal mostly with finite dimensional spaces. So in fact, this was, as for mathematical part, it will be just linear algebra. And there are more general states which are called mixed states. So you can view the points of phase space, which was introduced by Newton, but I have to add just no space. There was Newton, there was Lagrange, and there was Hamilton. The Hamilton presented the classical mechanic in the form which proved to be quite useful and convenient for the founding fathers of quantum mechanics to generalize. And so it was Schrödinger first who said that we need to describe the states, our system of the vectors of Hilbert space. Schrödinger himself, he didn't use this dictionary, Hilbert spaces, vectors. He just says that it is wave function. But it is, you can just view the function which satisfies the Schrödinger equation just as a vector in certain Hilbert space, and this is abstract. I'm not sure who was the first to pronounce these words, maybe Max Born. And there are more general states, mixed states. You view the points of phase space as a probability distribution concentrated in one point, just delta function. But you can use more general probability distribution, in fact, arbitrary. It was first proposed by Liouville, and now we say that so-called mixed states, they are just measures in your phase space. Phase space in the simplest case is just 6-dimensional space of coordinates and the momentum of a particle in standard particle, yes? So in the quantum mechanics, mixed states was, again, Neumann, in fact, just finished this, this formulation. The first was Dirac and then Landau, and finally, for Neumann, gave this general form. So we describe the states so-called density by using so-called density matrices with just the positive definite operators in our space. I'll explain a bit later for those who don't know, for people who do not know what is Okay, I'll make this notion a bit more detailed a bit later. So what are observables? In classical mechanics, we know quite well. It is just the function of coordinate momenta, functions, yes? And in the quantum case, these are Hermitian operators in the Hilbert space. So I didn't write here what a function we use. Of course, real world is real numbers. So we have to use functions whose arguments are the points of phase space, and that takes value as real numbers, yes? And in the quantum case, this will be Hermitian operators. Now, dynamics. There are two ways to embed the time evolution in your theory. One of them, you assume that observables depends on time, but states do not depend. This was Hamilton, in fact, and there are Hamilton equations, classical mechanics, but they are, in fact, it was again Newton, of course, who was the first. And as for the evolution of states, it was again Liouville who proposed this scheme. In quantum mechanics, as for observables, it was Heisenberg. First, he just considered, for example, the quantum oscillators were coordinate in the momentum. These are just operators in the Hilbert space, and they depend on time. And then, as for states, it was Schrödinger who first wrote his famous Schrödinger equation, and the abstract form was given a bit later by von Neumann again. And the last but not least, of course, is measurement, which combine both the observables and states to observe what are things that we measure. We measure numbers in experiment. So these numbers you obtain taking the observable equations, for example, the current operator that, and then we just current expression in classical mechanics, and you multiply by the distribution, you integrate that you make expectation of your observables with respect to the state. In quantum mechanics, you take your operator, you multiply by the state. This is again special operator, positive definite with of trace 1, and you trace this product. So let me now just a very short exposition of notations that I'm going to use. I have to admit that myself, I am not complete fan of Dirac notations. I am a bit more old-fashioned, using just, but they are quite convenient first, in fact. And the second, this is a kind of fashion in quantum information theory, which is now the most extensive fields that use this entanglement, etc. They are quite widely used. Therefore, let me show that the vectors, a vector is just the collection of complex numbers. But since they are complex, you can consider the conjugate numbers. And this is a bra, this is a cat. These are brackets which was introduced by Dirac. So we have the space is just you define the operation of excuse me, please. Operation of addition in multiplication by a complex number. And now so this operation of this quantum mechanical, in fact, term, superposition, And then you have a kind of product, but unlike superpositions that convert vectors to vectors, this you take to a pair of vectors and it will be complex number, which is definition via components. Yes, and again it is linear with respect to the second element and antilinear with respect to the one. And there is important particular case when you take inner product or scalar product of the vector by himself. This is called the square of norm, so a kind of length, yes? And now operators, again, these are just linear maps of our Hilbert space in itself, linear in the sense that it convert the sum into the sum, and you have two operators, again, you will have sum. This is standard description via matrices, and this is how we define the action of the operator matrix on the vector. It is just like that. Yeah, and there is a multiplication operation. So you have two operations, addition and multiplication. And this is a definition via components. This is a so-called row by column. Yes. And then let me show you several examples that we will use quite often. The first is simplest case. So excuse me. Here, so this we call the diagonal entries. They are all diagonal entries. Diagonal operator, just zeros of diagonal and some numbers diagonal. And there are four matrices which are quite widely used, called Pauli matrices. They are quite simple. The sigma naught is just two-dimensional unity, matrix unity, sigma 1 here, etc. You see. And it is very nice to these are simplest possible because one-dimensional matrix is just numbers. Two-dimensional matrix is just first non-trivial case, yes? And you can easily verify that if you multiply these matrices in this order and the opposite order, they are different. So in general, this operation, multiplication is not commutative, and this is somehow the measure of non-commutativity, which is called commutator, yes? Yeah, so we have this general technique which we are going to use, and we need a special class of operator called Hermitian operators. So you have a matrix of given an operator, you have its matrix, and you just transpose indices and make the complex conjugate. So why do we need Hermitian operators? It will be clear from that formula. It's called spectral theorem. So any Hermitian operator can be written as a sum of operators, simplest one. This is rank 1, just operators related, which are determined by two vectors. And you have the eigenvalues, and their eigenvalues are real. And let me remind you that observables, these are just Hermitian operators. We measure their eigenvalues, and they have to be real because you measure real numbers. Imaginary numbers were invented by Indians, but it is mostly for convenience. Eventually we have to measure real numbers, yes? And so the Hermitian operators, a particular case of Hermitian operators, positive definite operators, we need them because you may remember, as I mentioned, that the states in quantum mechanics just density matrices. Density matrices, these are positive definite operator of trace 1, which is defined a bit later. Yeah? So we have a rank 1 operators that are defined for any pair of vectors of our space. We define operators whose matrix is here, and it acts on any vector in that form. You see, you apply it to the vector, you get the inner product times the vector which is in front. Yes, and the particular case of rank 1 operator is orthogonal projections, and they play again important role. I'll just mention a bit later. So for Hermitian operators, I said already, but for Hermitian operators, you can define important for us things called, given any function which acts from, define it on the real axis and taking values in complex numbers, you can define a function of operator, just it is operator with the same eigenvectors but eigenvalues, they are just functions of eigenvalues of your operator. Yeah? And so this is a quite important fact which is called spectral theorem. Yes, and then you see the eigenvectors are real, eigenvalues are real, eigenvectors are orthonormalized, and the particular case, positive definite operator, which will need quite strongly later. This is just you write spectral theorem for them, and it will, because of they are positive definite here. And the trace 1, we have this property that all the eigenvalues are between 0 and 1, and the sum of them, there is no place equal 1. So the trace of operator is quite important operation, very simply defined. It's just the sum of diagonal entries. And if you about the function, and we will use it many times, so it is just you take eigenvalues of your operators, compute a function, and then the sum. Well, and these are standard things, but there is a less trivial part of linear algebra that we will need, which is called tensor products. Well, we have two Hilbert spaces, and we define the product, tensor product of two spaces like that. So this is a collection of complex numbers now indexed by two indices. One of them runs via the first space, second runs over the vectors of the second space. So this, as I repeat, it is just if you feel that you do not see it quite clearly, just recall the function of two variables. All of us, we know from the calculus that there are functions of one variables, two variables, etc., etc. So this is just a function of two discrete variables, and you can view, for example, the functions of two variables as a tensor product of two Hilbert spaces of functions on one variable. Yes. So, and in particular, you can take a vector from the first space, a vector from the second space, and you define the product, tensor product of vectors that are special elements of our space, having sometimes you write like that, sometimes after Dirac you write simpler, but their components are the products of components of two vectors. Very simple, yes? So it is tensor products of vectors. You can, if you have a space where the vectors are indexed by two indices, then the operators, matrices, have to be indexed by four indices, yes? So this is written here. So first, you see the first index here, and then this is standard way to, with 1 prime, it is just the first indices of first space, with 2 prime that, and the action of an operator in the tensor product on a vector on tensor product. It is just again like before, but now the role of the second index play a pair. So it is more or less simple defined, but just quite important. In fact, you needed to define the entanglement. Yes, and a particular case of operators in the tensor space is you take an operator in the first space, an operator in the second, and you define this tensor product of operators quite simply. So the first one has indexes of the first space, the second space, like that. And if you apply the tensor product of two operators on tensor product of two vectors, you'll get, so they act corresponding on its own space. So you have this formula. And in particular, it's quite interesting. Assume that you have one of your operators is one, just unity, then this operator acts on the first, but second is not touched. So you can just recall from calculus the partial derivatives. If you have a function of two variables, you take partial derivatives. This operation acts on the first variable, doesn't touch the second. Well, and the very important notion, which I am afraid that it is not presented in the books of linear algebra on tensor products, it's called a partial trace. If you have an operator from the tensor product, there are 4 indices which you need to describe the matrix. So you make first index here, second index here equal, and you sum. And you do not touch the second indices. So partial trace convert an operator from the tensor product from an operator just in the first space in that case. You can do the same with the second indices, etc. And again, if you have a product of 2 operators, tensor product, you apply partial trace, it acts on the first one, and the result, this will be the trace, and here still the operator on the second space. And in particular case, again, we will need it for our calculations in quantum mechanics. If you have a tensor product of 2 rank 1 operators, then making the trace, you'll get this inner product of that 2, and this operator is the same. Yeah. So it is just I repeat some little excursion in the linear algebra in the notations, and now let me go back to that scheme, and let me just it is not written here. So it is important to remember that we already had the pure states in quantum mechanics, just a vector of our state space. But we can view there is somehow almost one-to-one correspondence. You can replace the vector by rank 1 operator. If you assume that the norm of your vector is 1, then it will be just a projection. So we can view pure states in quantum mechanics either as vectors in Hilbert space or as rank 1 operators, and it is quite useful point of view. And so in that case, and if you recall the spectral theorem that I mentioned, so density matrix, it is just by spectral theorem, it is just the numbers positive between 0 and 1. And here you have the eigenvectors. Now, if you view every eigenvector as a projection, these things as a projection, it is in fact a projection. And then you see that Y, I mentioned that this is a mixed state, because it's just the sum of pure states. So we have pure states. If you take the superposition of pure states, it's mixed state. Yeah. And now, so we just a bit more details by using the notations that we introduced. So our pure states in classical mechanics just a point, and here again you can view a point in your phase space as just as a distribution, particular case of distribution, there's delta function at that point. Yes, and then you view any probability distribution like delta x minus x naught. Now you write mu x naught. And you see that this is a pure state classical, and you do a mixture. So these are mixed classical, mixed state. Yes. The same story is here. So you see there is a lot of, again, here it's clear, the operators. Now, what is the dynamics? In classical case, I said that this dynamics of observables was introduced by basically Hamilton, and it is written like that. So what is dynamics? Just you have to write, after Newton, the equation of motion for your either observables or states. So you have to write a differential equation, in fact. So, and here I do not define, it's called Poisson brackets, but it is just expressed via, so you have to know a certain function, which is called Hamiltonian, it's just the energy of your system, most important variable. Yes, and when you say that you have a system, in fact, you have to present the Hamiltonian of that system. And having the Hamiltonian, you write the equation of motion, which is in fact the differential equation. Here's the derivative with respect to time. Let me write what is a Poisson bracket. It is just the sum over degrees of freedom. Minus you change. So it is just, these are your coefficients, this is your function with respect to, you write the equation. So you see this equation of first order both in time and the variables and p and q, these are just points of phase space in general way, but the origin, of course, is a momentum, a coordinate of particles, momentum and coordinate, yes? And so it was due to Hamilton and states, it was due to Liouville, it's called the Liouville equations. It is equation for the density of our measure, probability distribution. In quantum mechanics, you have a similar formula. First, okay, you write again some equation. Now, these square brackets, this is just the commutator. Let me remind you. This is a commutator. It was before, but just so A, for example, it is just the HI minus AH. So you see, it is formally, and the last thing, okay, of course, so it is written here. So the measurement, you just compute expectation of your observable with respect to the state. And here you write like that, but it is, again, something similar because the trace is a sum, and it is just a discrete analog of this integral. So you see there is just quite schematically, just algebraically, there is a similarity on that scheme, and it was my intention to put that in that form, because you can ask, what is the difference? But I'll show several quite serious differences on the next slide. But before, let me say that, okay, in fact, the founding fathers of quantum mechanics, you can see from historical books, somehow they had in mind this scheme, in modern analysis of that scheme, which was done starting from the famous book von Neumann, Mathematical Questions of Quantum Mechanics, shows that there are two, in fact, even one fundamental difference. You have a scheme. Okay, I presented the scheme. You have states, you have observables, you have dynamic, you have measurements. And now, it suffices to assume that your observables do not commute, so just this in all other elements will come automatically by using certain mathematical theorems which comes from functional analysis. There is another scheme in which you can just assume that, okay, you have the first part. So you have, instead of these states, you describe your states as vectors in Hilbert space, and all other elements will come out automatically. So the scheme quite tightly connected, and despite that there is a similarity, there are hidden, roughly, differences, and let me make them a bit more explicit. So the first thing is called Born rule, and this is, okay, I'll start from the measurement, but because it's very important. So the measurement part of quantum mechanics, maybe many of you know, this most delicate thing, still not settled completely. There are different still proposals to interpret. Nobody doubts on the fact that it's mathematically it's good description of the nature, but as for related philosophy interpretations, there are still a lot of controversy. But myself, I am a bit conservative. I use the the interpretation of which was put forward by, in fact, basically Niels Bohr. It's called Copenhagen School, but we will not discuss this. It's quite delicate subject. So, but nevertheless, there is a rule which just concerns the experiments. So assume that you have an observable, it's Hermitian operator, and I would like to measure its eigenvalue, which could be, for example, okay, you have assume that your variable just a spin. You would like to measure the components of spin, yes? Or just coordinate, or just momentum of your particle. So I wrote the equality with a dot because, you see, here is operator is a number. They couldn't be equal, but in fact, it is just a probability to measure that your observable is given to this number in that state. And according to the Bohr, it is to Bohr, this is the following. You take the corresponding eigenvector corresponding to the value of physical quantity which you measure, and you do the scalar product square of this eigenvector with your state. You assume that your system in the state psi. It seems quite simple. By the way, it's Nobel Prize by Max Born for that formula. Yes, and so it is the first thing that I would like to show, this Born rule, and it's analog of when you measure coordinate and momentum, you use, I don't know, whatever you can use, the microscope, the ampermeter, whatever. Yes, and the second quite serious distinction that I repeat, I mentioned this already. The classical observables, they commute. Quantum do not commute in general. And if they do not commute, they produce so-called uncertainty principle put forward by Heisenberg. And this is the first, okay, this is maybe most famous unusual property of quantum mechanics. Yes, the coordinate and momentum, they satisfy the uncertainty principle. Third things which quite, it's quite innocent thing. You say that your states are the vectors in Hilbert space. But since you use this notion, this mathematical notion, you have to interpret and you have to use the sum of two vectors, because it is a basic property of Hilbert space. And in quantum mechanics, it was, I believe that it's Dirac first said that we'll call it superposition principle, just the rule that if you have two states, you can add these two states. Let me, this addition of the vectors, not a probability distribution, produces a basic difference of quantum and classical mechanics. Let's consider a very simple example. You will see the meaning of these two words a bit later. So assume that we have two states. What are the states in classical mechanics? Just measures. That means there is a density. This is non-negative function, and its integral equal 1 because it's probability distribution. You having two states, you can, of course, write the state which is the sum of two states. Why? But you have to put 1 over 2 because what are states? I repeat, just any measure on your phase space called state. But the measure of total mass 1 sees this to mu1 and mu2, the integral equal 1. To have the integral equal 1 for mu, you have to put 1 over 2. Now, what is analog in quantum mechanics? Let's confine ourselves to the pure states. You have two pure states. Assume that they are orthogonal. That means the scalar product is 0. Yes? And in the norm is 1, each of them. So it's easy to check that this vector of Hilbert space, you are allowed to make sums. It's also a vector of Hilbert space, and its norm equal 1. It's easy to check because of orthogonality. So it is a pure state. Any vector of Hilbert space of the norm 1 could be a state of certain system. This is the axiom of quantum mechanics, yes? But let's look what is going on because of Born rule. Well, classical assumes that you have just a particle. So what is going on? If if you are in state mu, you would like to know the probability distribution of your particle, and this is a measurement. So the probability, if your mu is a sum of two mu's, then you have this simple formula. So probability are adding in classical physics, yes? In quantum physics, the probability, if I have a, excuse me, let's go back. So I remind you that our state now, but not 1/2, square root of 2. Yes. So, and we would like to know what is the probability to find quantum particles in a certain little domain of our space, being in state psi. So it is by Born rule, it will be just square of our states. This is why there is a name, especially in old books in quantum mechanics. They call the state, if you just describe your particle in Hilbert in usual space, it's after in fact Schrödinger in Born, you call psi the probability amplitude, because the probability is a absolute value squared. So if you compute this vector, because it is a sum, you get this term, and the third term, which is, and the first term by the Born rule is just the probability of the first particle to be in the neighborhood of x. The second is second, but there is a third term, which is here. And now we can always write our states just it's called in the polar form. So it is just an absolute value times a phase. And the absolute value is the square root of probability, of course. So we write our every state in that form. And then you see, because of you have this psi1 conjugate, you will have, when you compute, you will have the product of absolute values times the exponent where the phase like that. And choosing, for example, the phase either 0 or plus minus 2 pi, you'll get the sum of probability like classical mechanics. But if the difference of phase is pi, then you will have the difference, which is completely new thing. And if P1 equal P2, you have 0. And it is an absolutely unknown fact in classical mechanics, but it is well known in classical optics, because there is a superposition. If your two waves in phase, they add. If you are in anti-phase, they destroy one another. So you have, this is why, by the way, I believe Schrödinger called quantum mechanics, it's not him, he called wave mechanics. Because he was first saying that quantum particles is in fact a wave. Well, it's more or less known things. Now let's go to the most. I believe that we have to make a break, or no? Huh? Yeah, just 5 minutes. Yes. Or whatever, if you allow, you can continue with Ukraine. Okay. Well, you know, in Soviet Union we have not like in Anglo-Saxon 50 minutes lecture. We have like in France we call two academic hours, 45 minutes with a break 5 or 10 minutes. But the difference with France was that in Soviet Union there was the bell in any university, because people who are doing lectures, they do not recognize the time, so there was always a bell. Well, so we have this important thing. Now let's go back to our subject, and let me define more advanced notions, which are in fact has been known since long time, but they became très à la mode just in recent 2 decades, maybe. The first, bipartite system. You have a quantum system consisting of 2 parties, even they say. What does it mean? For example, 2 particles, or 2 spins, or maybe, I know, like in black holes, black hole and its radiation. It's quite general notion, but important thing that if yes, then the state space of bipartite system by definition is a tensor product of state spaces of 2 parties. And this is why I need the tensor product, and why I describe shortly the properties. Yes? Well, and now we have a certain state, certain density matrix of our composite system, which could be viewed as a co-analog of quantum analog of, assumes you have two random variables. There is a lot of analogy with probability theory. Some people even call quantum mechanics quantum probability theory, but it is not the case because of superposition principle, not just quantum probability. So let me remind you that if you have 2 random variables which assume values, for example, with probability, I know, p, j, q, j, yes, then in general, if you ask about the probability of the pair, it will be the probability, corresponding probability will be a function of 2 variables. This is a joint probability called. But if myself, so we have all these numbers between 0 and 1, and some standard things in probability. You have a joint probability, joint probability distribution. If you would like to, if you are not interested in the second variable, you are working only the first one, you produce a marginal. So you sum your joint probability with respect to the second, and now it will be this probability. But in general, you have to describe a pair of variables, you need the both. And there is a special case when this probability is is factorized. And it is called if we have the situation, we say that our system, our pair of variables, they are independent, statistically independent. So we have more or less the same in quantum mechanics. We have a density matrix of our bipartite system, which is in fact probability distribution of a pair of variables. For example, you have 2 particles, each of them they coordinate and momentum. You have to describe the both, yes? And well, then we form the analog of marginal, that we just take this density matrix and you trace out the degrees of freedom corresponding to the second system. This is by using you remember I said this is partial trace, and we get the things which is known as reduced density matrix of the party SA, and it is quantum analog of marginal, yes? And now the basic definition, so we say that pure state of your bipartite system is entanglement if it is not a product. So it's exact analog of the independency. So the system, we say that the system, the bipartite system is entanglement if its state is not a product. So if it's probability, but not probability amplitude. You have to remember this important difference. But nevertheless, this is definition. So it is very simple. As I say, you can even somehow wonder why it took 10 years. The quantum mechanics was basically made during a year 25, 24, 26. And it took 10 years for Einstein, it was Einstein first just understood that there is a certain analog of this notion which plays an important role in quantum mechanics. This means entanglement. By the way, the name entanglement was invented by Schrödinger. I mentioned Schrödinger in the very same year. He wrote a paper just following the famous paper Einstein-Rosen-Podolsky about incompleteness in quantum mechanics. He said that it is a very important notion which, in fact, main difference between classical and quantum mechanics, the notion of entanglement. Yes? And this is for pure states. If you have a mixed states, then you say that it is the analog of that state is a bit more complicated. It is not just the tensor product of two, but you have to take a sum still. There are certain quite delicate arguments that shows that you have to use you have to call the not entangled or separable states not entangled, not just which are not tensor product like there, but a bit more general. Nevertheless, these are two well-written, presented definitions, and now we are going to consider how do they work. Okay, so we have it's very nice. This is I mentioned the Schrödinger recognized very important, that the entanglement very important positive notion, and it is his citation from his paper of 35. And I need two more notions which I will use. The first is the coherence. It turns out that entanglement is quite subtle phenomenon. It's very simple to destroy by classical environment. And the corresponding, so as an influence of environment, your coherent system living in entangled states becomes, the entanglement deteriorates. And this corresponding process has general name of the coherence. And I'll need, on the next lecture, I'll need the notion of qubit. I mentioned already this is simplest possible, non-trivial quantum systems, just in two-dimensional space. And you can use the basis on that space. It's again commonly used notation. So you have two basis vectors in that C2, and one of the first one we denote like that, and this like that. Yes. So it is again. So one more, notion, explanation or definition of entanglement by using everyday words. It's written here. So you have your system, for example, bipartite system, you'll see a bit later. It is in pure state, and but two subsystems, two particles, they have no pure state. Their state is common, and it is not factorized. And these things is impossible in classical mechanics. And this is why it is important. It's easy to see that from the formulas that I wrote, it is clear that if in classical mechanics you have a pure states of bipartite system, so the states of, and you trace out or integrate out one of the variables, then you will get again pure system. Here it is not the same. So a natural question after this quite simple mathematically, but we are going to see quite non-trivial physically definition of that phenomenon. So it is just not a product, just a quantum analog of dependence. Yes? And the natural question which arises immediately is the following. Could we quantify entanglement? So you have we have amperes, we have volts, but we have ampere meters and voltmeters. So we have volts and amperes to measure, to quantify electric current. We need something like that for that phenomenon which is so far was described just qualitatively. We need a quantification, as they used to say now. And the most important quantifier, that means, what is a quantifier? It is just the sum, excuse me for mathematics. So you have you have a space, you have a, not space, but you have a collection of your Hilbert space. In your Hilbert space live the density matrices, positive definite operator of trace 1. Now they describe the states. We give a definition of the states that are entanglement. So we have to invent certain functional, that is a map of the, that acts on a positive definite operator of trace 1 to the real numbers that allows us to conclude whether these states entanglement or not. Yes? We say that, for example, that the quantifier of electric current is just ampere meter, or volts, or amperes. Like here, the same is here. And the first and mostly known and used, the quantifier is a von Neumann entropy. So let me just give a definition for general case, not related to entanglement. So it is, by the way, the von Neumann introduced this notion. I repeat, in some particular cases it was already invented by Dirac and Landau, but general form was given by von Neumann. So he introduced, given the density matrix, just a state of your quantum space, you define this function, which is in fact a positive, non-negative number, written as here. You take your density matrix, you compute the function of the operator. This is why I gave a definition of the function. Logarithm of your density matrix. I repeat, this is a function of the operator. Yes? You multiply them and you take trace. And if you, it's easy to find by using definition of trace that if your rho, like here, you write rho as a mixture of pure states, then the entropy will be just this simple function. Yes, yes. And by the way, it was okay. And in that form, by the way, it is almost coinciding with a quantity with completely different field, because this was done in 35, and in the somewhere in 50s, Shannon invented information theory, and he introduced the entropy, completely different reason, but in fact this is written in that form. This is a Shannon entropy. Well, and it's easy to check that if you have a pure state, so it is a pure state. Pure state, it is just a projection as I wrote before. Yes? And a projection, let me write here. And I wrote the form of the projection on the state. It's easy to check. It has property. Yes, this property. This is Hermitian operator such that the square is equal 1. And it follows that the eigenvalues of pi psi, they could be only 1 or 0. And in both cases, this quantity is 0. So if you have a pure state, your entropy is 0, and a bit more complex to prove that the converse statement is also valid. So we say that, okay, by using mathematics terminology, we say that the entropy of quantum state is 0 if and only if the state is pure. Yes, and on the other hand, if you have if you take this, okay, so I repeat, this is just the entropy is just a number, non-negative number, and assume that let's compute the maximum of this number with respect to all positive definite matrices of trace 1. It's easy exercise. You will find that the maximum is equal to the logarithm of the dimension, and the corresponding density matrix which produces the maximum is just unity matrix. But since the unity, of course, is positive definite, to make the trace 1, you have to divide by dimension. So it is a density matrix, but it is easy to see that it corresponds. So it is a particular case of that formula, in which every pt is just 1 over n. So all the states are presented the same weight. And it's natural to view these states as a maximally entanglement state, because it's absolutely no product. All the states presented in on the same footing. So it is mostly, and we can say that the von entropy is a quantifier of the mixedness, because it allows us to conclude whether your state is mixed or not. But okay, what is the advantage? Because it is simple, in fact, because to find an entropy, because of that formula, it suffices to find the spectrum. So it's an algebraic problem to find the spectrum of a given matrix, positive definite trace 1. So it is algebraic equations, yeah? It is faithful in the sense that it is quite exact, yes? And it's important that it is invariant with respect to unitary transformation, because, of course, our results should depend on which basis we compute our operators. It's natural thing, yeah? But moreover, it turns out that if you have a bipartite system and you compute the reduced density matrix of the party A, by the way, it's a common fashion in quantum information theory. We say the system A is Alice, the system B is Bob. Okay, it's a fashion. Yes, and okay, we have a state of them too. Then we compute the reduced density matrix of the party A of Alice, and then you compute its, not complete, but just of that matrix of the reduced, compute its von Neumann entropy. It's called entanglement entropy. And now let's make a simple exercise. Let's take the state written here. So we have two spaces, both for one. It's in fact the state space of two qubits, because I mentioned already that the simplest state space of dimension 2, it's called qubit state. And we have two qubits. But now bipartite system is just the system of two qubits. By the physical implementation of qubits, for example, spin of electron, 1/2 up and down. Yes? And then let's write this state, just a superposition of two basis states, yes? And it's okay. It is the simplest example of entanglement state, because you see, and it shows you the power of superposition principle, because every term is not entangled because it's tensor product, but the sum is always entangled. So just because of presence in quantum mechanics superposition principle, you have this phenomenon of entanglement, yes? And yes, and it was, by the way, it is strange enough, it was proposed first by Bell in the 60s. And I asked myself, I have this pure state. We have seen before that for any pure state, the entropy is 0. So the entropy of your states is 0, minimum. So the state is not entangled. Yeah? We see. Now let's pass from this pure state, and it's the corresponding density matrix, just a projection, but it's operator in the tensor product of two-dimensional space. Let's compute the corresponding reduced density matrix. Therefore, we have to trace out the degrees of freedom corresponding to the system B, and it's easy to find that this reduced density matrix, it is 1 over 2 of K. But so it is maximum entangled. And you see that just this innocent procedure in a very simple state is able to produce this phenomenon, yes? And so we can say that, and of course the entropy, so the entropy of that state is 0, entropy of that state is maximum, just 1. So we can, this is a motivation to use the entanglement entropy as a as a quantifier of entanglement. By the way, it is a name. So we have a quantifier for our a simplest one. In next lecture, I'll show 2 more, even 3 more quantifiers, which are different and important also. So, but now we have our first entanglement quantifier, which called the entanglement entropy. It is just von Neumann entropy of reduced density states. So we have still 20 minutes. And let me show you, because it's maybe too abstract, too formal. Let me show you a simplest application with, it was invented so this application was with respect to the rate of the speed of development in quantum information theory. It's ancient time. It was invented in 1993 by physicist Don Page, former student Hawking, who just proposed to describe an important phenomenon called Hawking radiation by using some random elements. So we are coming to the subject of my course, because it was written that it is just entanglement disordered systems. But let me remind you that even classical probability has, roughly speaking, 2 origins. 1.5. So the most important origin somehow, one of the most important origin, when do we say that we need probability or something is random? First of all, it is in the case we don't know what is going on. If we do not know what is going on, we say that this something that is going on should be random. And we can even remind ourselves that if we know statistical mechanics, the Gibbs distribution, Gibbs made the foundation of statistical mechanics. Before there was Boltzmann, Clausius, Carnot, but it was just very important application. General scheme was invented by Willard Gibbs in 1900, and he just said that our system, the energy should be conserved, yes? And so now our phase points, our state, our system lives on the surface of fixed energy. But where does it live? We do not know. So we assume that with equal probability, it could be at any point of this surface. It's called microcanonical distribution. Why at any point? Because, look, because of complete ignorance of the situation. We do not know. And so in the situation which we can say anything about where things is living, we say that it lives in the black box where any options, any behavior is equally probable. So, and this is philosophy roughly was used by Page. So what is a phenomenon? Black holes were known even, I believe, Lagrange or Laplace already in classical physics. In quantum physics, it was roughly it was born by thanks of efforts by Hawking. So because he said that black hole, if it is quantum object, there should be radiation, and it's called evaporating of black holes, or Hawking radiation. And to describe this phenomenon, Page proposed, let's view the black hole and its radiation as bipartite system. Yes, and we are interested to know what is going with let's go back. When the black hole was born, it just started to radiate. And let's try to describe this process of evaporation, at least on the initial stage of the process. And the proposition was very simple. So since it is a bipartite system, we just assume that it lives in the tensor product of space. A is a radiation, B is a black hole. And the dimensions of that space is like L and K. And dimension of our space, of course, is a product. This is here. And we know nothing. It's black hole. Excuse me for the calembour. Black hole is a black box. Yes? So we assume that the state of the black hole is pure state, but it is just the vector which is uniformly distributed on the unit sphere in our space, sphere in our space. So our space is dimension k times L. So we write, because it's tensor product, we have to index it by a pair of indices. And this is a vector index whose components are indexed by the pair. And since it is, okay, it's like that, so we assume, so the only restriction on the components of that vector is that their sum is 1. So this is, otherwise, so the probability is just uniform distribution over the sphere in this multidimensional space, yes? And, well, if we would like to describe now the corresponding density matrix, since the state is pure, let me remind you that the pure state is described always by the projection, orthogonal projection. And orthogonal projection, if it is psi, so it's matrix, just the product, psi j, psi k conjugate. So this, and the entries of projection, these are just products, yes? So we write the product, but in tensor space, and it is what I have written. So the matrix of our pure state, in which we assume the black hole was at the beginning of this evaporation process, maybe, I don't know, 100 million years after, just after Big Bang. So we have this density matrix. And now we would like to write, corresponding to our philosophy, we have to find the entanglement entropy of that thing. So what does it mean? So our system which we are interested in is A, radiation, B is a black hole. Since we are interested in radiation, we have to trace out the degrees of freedom of the black hole. So we just make this K1, K2, these are indices of black hole, equal and sum over them. And this is our state, our reduced density matrix of the radiation. And now we would like to compute, we have to know the amount of the entanglement in that, in the radiation. So, excuse me, I forgot, here minus. So we have to compute just entanglement entropy, since which, as we decided just now, is a quantifier of quantumness, of quantum correlations in the radiation. Yeah? Well, okay, I have 2 minutes. Let me just show you. So it was just a nice problem, nice posed problem. What do you have? We have a now let's view this vector not as a vector in the tensor product of two spaces, but like a matrix on the usual space, because there are two indices, yes? And then, so we have this matrix, excuse me. So let me see, here. So we view this as a oh my God. We view this vector as a matrix, but rectangular matrix. We just construct from the rectangular matrix the square matrix where indices are L1, L2. These are degrees of freedom of the radiation. And now we have to compute the trace. This well-posed problem of random matrix theory, because the psi is random, uniformly distributed over the sphere. We have to compute these things. So Page himself, he just wrote absolutely, well-defined problem But he said, I don't know what is the solution. I just computed 1, 2, 3, 4, and he proposed the formula. But the formula for the expectation, because we are coming to a very serious moment. So now our state is random. But here is a mixture of two randomness. There is a classical randomness which comes from the complete ignorance or partial ignorance. And there is a quantum randomness which comes from the very, basic definition of quantum mechanics, because in quantum mechanics, unlike classical mechanics, quantum, this is not the measure of ignorance or a description of ignorance. It is just the intrinsic property of quantum mechanics. Yes? So we have, but this is so the object is quantum, this is density matrix, but it is random because of our ignorance. It is just our subjective description. Yes, and we have to compute the eigenvalues of that matrix. Because, let me remind you, because the entanglement entropy is just, if you know eigenvalues, you just compute this sum. So we have to compute the eigenvalues, and just playing with matrices of the dimension 2, 3, 4, and making the expectation with respect to the, integrating over the sphere, Page was able to write this formula. He said that my conjecture, this formula is valid for the matrices of any size, and this is a formula. And then it was quite fast proven by 3 different groups of researchers, and now this is a formula, and it's exact formula, but it is not necessarily to know, in fact, this formula exact, because we were interested. Black hole is quite big, so we of course assume that K is big. So we have to know this answer. So this is exact formula, but we have to know its asymptotic form when K is big. L is not necessarily big, because if the process of operation just started, L is a number still. But it could become big, but not immediately. So we keep L fixed, and we assume that K is big enough, and then you compute easily this is just, you from the book, easy to compute this expression, and you'll get the formula with 2 exact terms and some error estimation. You see, the leading term is log of the dimension of your black hole, and this is the correction. And let me remind you that if you have an entanglement entropy or entropy in general, it is a maximum when you compute the entropy of the unit matrix. So and it is log. So from that you conclude that it is a conclusion of Page that this formula shows that at the beginning of the process of the evaporation, indeed, so our black hole in the pure state. And then there's a certain correction, which is called deficit. This is the second term, which shows you in which direction. So you have a minus. Therefore, of course, it's intuitively clear that your black hole was at the beginning. It was in the pure state, and then this state is becoming deteriorate just because of radiation. Yes. So we have this property, but it is only the mean. And if you have, it is written in red, just because I would like to stress this point. So our object, the density matrix, is random, and we are able to compute the expectation. And it's common sense of probability theory. So if you have an arbitrary random variable and you know its expectation, you know just a little, almost nothing. Because if the distribution is not sharp, if it has wings and large wings, then the expectations say you just a little about your random variable. So Nevertheless, it was a big, large amount of papers playing with these things in many aspects. And then eventually people came to the question, what about fluctuations? Because if fluctuations of your entropy are big, then the knowledge of the expectations say you almost nothing. You have to think about computing for example, the fluctuations. So, but nevertheless, I believe that it is a good point to finish because, there is one more slide. So we have this conclusion. Well, and it is just a more detailed form of previous slide. So there, in the very beginning of the evaporation, you need even the first term. You see that in the very beginning you have this log, yes? We have this formula, which is valid for any, what is going on, my God. Which is valid for any L. The only parameter with respect to which we compute asymptotic is K. If we have this formula, at the very beginning of the evaporation process, we can neglect this term. So L is fixed, K tends to infinity, and you have just a log, and you say that, okay, you are almost in the pure state. Now, you can consider a next stage if you want. So you assume that K tends to infinity, but L also tends to infinity. And the ration, roughly speaking, it is already the stage of the process where radiation is a non-zero fraction of a black hole. Yeah? And then you have this formula, and you have a good expression for the deficit. But everything, of course, still in the mean. In the beginning of lecture, next lecture, I'm going to show you that this formula is valid. In fact, it's probability 1. So for any typical realization of your black hole, and it is somehow a final answer which we would like to have, because after that you say that it is valid almost for any typical realization. Therefore, it is more or less reality. Well, thank you very much.